oil, let's say, and some water that is pushing the oil. And because of the difference of ratio in viscosity, you have this viscous fingering that occurs. And so this is an example where you have an interface that is moving between two phases, where you have some pretty thin details that develop, and you want to be able to capture those details. And this is where adaptivity with the Octree can be useful. So this is the exact same simulation, but I just show the evolution of the interface. And you see that the mesh is adapted automatically where the interface is. So it looks like blue because it's very, very refined, but the interface is red. So like Vincent said, the advantage here is, the meshing is trivial, but it's not body fitted, and which means that here you have to work harder to impose the right boundary conditions. Whereas in the other approach, the boundary condition would be trivial, but the meshing itself is harder. So we take this approach. So in the case of, so that's what I wrote a little bit here. So this is an example of an Octree. So this is general mesh. This is a very simple mesh where you have the entire computational domain that you associate with the root of your tree. And every time you split into in 3D, you add a generation of children, okay? And the advantage of this data structure is that you can get to the leaves, which are the smallest cell, where you actually do the computation in log of n algorithm, where n is the number of grid points. And so in terms of the meshing here, when I say it's trivial, it's really trivial. It's really one line of code that tells you where to refine, because what we use here is a level set function. I'll discuss that a little bit later. And the level set function is Lipschitz continuous. And so if you write the mathematics of what it means is, this is the refinement criteria. If you have the value of the level set function at any node of your grid that is less than, this is the Lipschitz constant, so it's a number. Usually it's 1 because you take a distance function. But depending on how you tune this parameter, you can have a grid that is graded or not graded. And then the diagonal size of the cell, this is just the length of the diagonal of one cell. And so if you have that, you know that the interface is there, and this is where you refine. So you cut the grid into 2. That's it. So it's very trivial. All right, so Octree is not new, okay? It's been done for quite a while. It started with computer graphics. It's at the base of the fast multiple method as well. In terms of applying to Navier-Stokes, I think Stéphane Poppinet was the first one, I think, who did that. And so when you solve equation on Octree, the first question is, where do you store the data? And this is actually an important question. So if you do some fluids, usually you use a staggered grid, okay? We have the pressure at the center and then the velocities at the cell faces. But of course, you can also store the quantity at the nodes. Okay, and you have advantages in depending on what you try to solve. And so in the case of fluid, you do want to use this magrid arrangement for Octree because it's very easy to to discretize a gradient operator and a divergence operator in such a way you have this property. So this property is something you have in math, okay? Gradient is minus divergence of transport of the divergence. And if you have that, you can write L2 stability that shows that the projection method is stable. So if numerically you can have a discretization of the gradient divergence have this property, then for sure it's going to be stable, okay? And so in this case, it's trivial to write a divergence when you have a grid like this. It's fine volume, okay? And once you have this discretization, you just take the transpose to define your gradient operator, and the scheme will be stable. But there are a lot of other equations than fluids, and even when you do some fluids, you want to solve the energy equation, for example. And for that, there's an advantage of doing stuff at the nodes. And so the first person who did things at the node was John Strain, where he did the level set, an advection, simple advection equation advection equation, actually, that was just what he did. And so he was saying that on an Octree grid, it's an advantage to use a node-based configuration, because if you use, for example, a semi-Lagrangian, that tells you to trace back along the characteristics and end up somewhere. and then interpolate from the data that you have in your cell. If you use a node base, then it's completely trivial. Wherever you end up is definitely within the cell. And you can do some linear averaging to get the value of the cell, wherever it is, using the surrounding values. If you were, on the other hand, to start from the center and do a backward characteristics, using the other value at the center, you would have to do some sort of triangulation. That's something that is harder. So we got the idea of saying, okay, well, can we go a little bit further if we store things at the nodes? And the first question we had to answer is when you have an octree, you have so-called T-junction. So T-junction is when you have a neighbor that doesn't really exist. So here you have a neighbor on top and bottom of this vertex V0, but you have one missing here on the right side. And so you need to define these values somehow. And the first idea, of course, is to use a linear interpolation between the two adjacent points. But then we notice that we can play this trick here. If you do a Taylor analysis of this approximate ghost value, if you do Taylor analysis with that formula here, you would have that you have the exact value that you would like to get, plus, of course, some error. And this error, you have this O of delta x cubed, so delta x is the size of the smallest grid. And then, unfortunately, you have this term here on the way. Okay, so you don't have a third order, you just have something that's second order. However, if you store things at the nodes, if you have one node that is missing in the, for example, x direction, then for sure the points in the y direction are aligned. You have those points. And those, thanks to those 3 points, you can do good approximation. In our case, that's exactly what you want. You want to have a good approximation of this phi yy term that is on the way to get higher order. And so you can approximate this term like this, and at the end of the day, that's how you define your ghost point. If you define the ghost point like this, then you have an approximation that is third order. And then you can use any kind of scheme, central differencing, upwind, etc. And as if the grid was uniform, and you get solutions that are second order accurate because of that. Another advantage when you do this thing is it only uses 2 adjacent cells, and that's something that's interesting when you do parallelization, because having access to cells that are farther away is computationally expensive. In 3D, so it looks more difficult, but it's the same idea. You always have 3 points that are aligned, and thanks to those 3 points, you are going to correct for the error you do in other direction. So that's the formula, and that's it. In this case, you have 3 adjacent cells. All right, so let me show you an example of what you're getting here. So on the grid, wow. On the grid that is fully adaptive here, so it's non-graded, that is the ratio between a cell and an adjacent one is not constrained by any factor. You can have very, very small cell next to a huge one, and you get the same kind of result. The linear system is non-symmetric, which is something that, when you're a mathematician, you don't like that much, but it's still an M matrix, so you will find a solution. The good thing about it is the solution is second order accurate. This is the L infinity norm, but also the gradient is second order accurate. So you get this superconvergence effect, which is useful. So for example, if you do something like this, which is a Stefan problem. So Stefan problem is, model for solidification, things about, snowflake that is growing. So here, this is a snowflake that is circular and is going to continue being circular. It's called a Frank sphere. If you start with the right parameters, you can get an exact solution that is stays a sphere. So this is an example where I want to show the difference between what you get on a uniform grid and what you get on an adaptive grid. The commonality between those two grids is the smaller cells that you have here on the interface is the same as the cells that you use on the uniform grid, okay? And if you look at the difference of error that you have, they're pretty much the same. It's about 10 to the minus 4 in L infinity norm. And this is not a surprise, because this problem is parabolic, so parabolic problem, the solution is smooth, except where you have a kink, and here you have a kink next to the interface. This is where you impose the condition. And so it's not a surprise. You can get by with a grid, a background grid that is kind of coarse, as long as you resolve enough next to the interface. And the error you have is maximum here, and you do the same kind of job, on both ways. But the solution you have here, you don't need this resolution here, okay? And of course, what you gain is since you have many less grid points, you have a linear system that is much, much smaller, and so the solution is much faster. We've developed also the entire level set technology on the sort of grids, and everything is node-based. So even if you have a velocity that depends on the level set function itself, which leads to a nonlinear equation where you have to use the right Godunov scheme, etc., you can do as if it was uniform. So probably no level set, right? I mean, if you represent an interface here as the cross-section of a higher dimensional function, and the only thing you have to do is pull the function down to get the change in topology. That's the big advantage. The disadvantage, of course, is the loss of mass that you have. That's an example where you do this sort of simulation where you start with a disk, and then you move into an incompressible velocity field. And when you come back, you get the blue one or the red or the green. The green is completely gone. Okay, when you come back, you lost everything because of loss of mass. And so this here is an attempt to get rid of it. Don't get rid of the entire loss of mass. It's still there, but it's within a few percent of a percent. Okay. And then so we wanted to do this thing one step further to do that on parallel machines. And the first question you want to ask when you do parallel work is how you partition your domain. So partitioning your domain is you're going to say, okay, all the yellow here is going to be to one processor, the green to another processor, etc. And you want to do things such a way they all have about the same amount of work. Okay. What you don't want to do is what you have on the road, what people are working. I don't know if you know this. You have one guy with a shovel, and then you have 5 people around there looking and waiting to do something. You don't want to do that when you do parallel computing. So the partitioning here is actually coming from the group of Gadas with our colleague PDE. So what they have done is they have created a library that is based on the so-called z-ordering. So the z-ordering, so just look at, maybe just that portion, K0. K0 is one tree, okay? And it's split into 4 big cells. And the z-ordering is going to go from this cell to this one, to this one, to this one, etc. Except that if you get to a cell that is itself split, then you do the z-ordering in that cell as well. And so the beauty of doing things like this is, and just recording just the leaves, okay? The beauty of it is that, like you see, it's contiguous. All the yellow is together, the green is together, and the red is together. So that's it. Partitioning is right there. And it's fairly simple to do. So they have done this. And so what this library is giving you is a list, a one-dimensional list of leaves from which you can reconstruct the tree. So what we do is, this is the complete mesh that you have, different colors at different processors. And then what we do is each processor is going to reconstruct its own tree in such a way the leaf of the tree matches what is given with the algorithm of PDE. And so you see here, you have a lot of grid points in that region, but the red processor doesn't care. It just computes this big cell just to have the tree structure. Okay, and thanks to tree structure now, we can solve all the equation we do otherwise. So that's basically the handshake between the two. So an example, this is absolutely terrible, but so that's an example of the same problem where you rewrite that thing in 3D a lot of time, but because you have a bigger computer, you can rewrite a little bit more. And again, an example where you have, so the black is the entire computation, and the green is what the green processor has. So it only computes on this amount of data instead of everything. We've applied this thing to some problem where we solve not just the level set, but here this is again the Stefan problem, so crystal growth. We've shown that it does scale on up to 4,000 processor. That's the limit that we have, and so this is a problem that is nice to showcase what you can do, because again it's parabolic. So if you look at the heavy lifting happens here near the interface. This is where you want to put a lot of cells, okay? And so as long as you capture here what is the thermal boundary layer, you're fine. But if you have a crystal like this, and then you have another crystal that is very far away, it looks like it's huge computation, and it's like it's amazing, but what you do in between is that you shouldn't put a lot of work. So this is actually a showcase that is It's in my favor. We've done that for the Navier-Stokes equation. So again, with the scaling. I haven't talked on how we do viscosity, but the viscosity is actually something that takes quite a long time, which is bizarre. Usually we think about the Poisson projection, takes the most. And the reason is because on this sort of grid, you have to construct a Voronoi partition to do the viscosity properly. And so that costs quite a lot. All right, so the thing I want to talk about here is a little bit the Gauss fluid, revisit it. So the Gauss fluid for the Poisson equation is you solve Poisson, you have a jump in the solution and the gradient actually in the flux. And the idea of Gauss fluid is to have, so you have one real fluid here, this is air, and you have water here, and you have a jump in between, for example, a jump of pressure. And the idea of Gauss fluid is to try to avoid taking derivative across an interface because you have all of one air. And so the idea is to take a Gauss fluid that has the real fluid plus the jump. So then when you do the derivative, you don't get big errors. Okay? So that's the idea. And so it's something that is quite successful. However, when you go to 2D and 3D, you split things dimension by dimension. And the problem is that the condition is given here on the flux is in the normal direction. It's not on the Cartesian direction. And so what Gauss fluid has done is they take the projection on each axis. And they say that you miss the tangential component, but at least you get the normal component right. And that is good, but the solution is convergent, but not the gradient. The flux is not convergent. And so the way we fixed that was to do the following. If you have, I'm talking about Cartesian grid. The way we solve that is we take all the points that are near the interface, we find their projection, and then we introduce 2 degrees of freedom on each side, and we take a distance delta x over 5 because we wanted that. And then with those points, we construct a Voronoi partition on each side. And so the beauty of doing this is that now you can apply Gauss fluid here because it's a 1D problem. So here you can apply the jump. There's no problem of missing the tangential component. And then you do that, of course, with a standard finite volume. And so that's the example where you have the Gauss fluid method. So the slope 2, second order for Gauss fluid or for the method I just mentioned. But when you look at the gradient, that's Gauss fluid. Gauss fluid does not converge. Whereas this Voronoi, we call that Voronoi interface method, does converge to first order. So on Cartesian grid, Gauss fluid is dangerous. It's misleading for projection method. And same thing for 3D, even with a large ratio of beta of 100,000 here. All right. Last little trick I want to show is in a case where you are interested in the effect of surface tension. And surface tension, for example, when you have some surfactant on the bubble, changes surface tension. And so we're interested in looking at this problem. So what you want to solve is the equation for the level set. U here is coming from the fluid velocity. You have an advection diffusion of the concentration of surfactant in the bulk. And then you have an interaction between the bulk and the surface by a source term. And the source term, depending on the type of kinetic that you want to use, usually it has a form like this, where this gamma is the concentration of the surfactant on the interface. Gamma infinite is the packing one, how much you can put in. So far so good. And then you have this problem of the transport of the surfactant on the interface itself. And here the problem is you want to solve a PDE on an interface, not on the Cartesian grid. And I'll show you how we did that. And then we have to link that to the Navier-Stokes equation, to the formula that relates surface tension to the surfactant, etc. All right. So the trick is the following: is to solve this equation here on an interface, is to take a uniform grid around the interface, a small grid, and then extend the value of the surfactant in the normal direction. And then you just apply the regular gradient and Laplace in Cartesian coordinates. And because you have extended things in normal direction, when you take the gradient, you basically cancel the terms that you would have to add. So that's an example of just that thing here, where you have a weird shape that is expanding, and so the surfactant is getting redistributed, and the four, those are different times, and the different curves are different resolution that do converge to the exact solution. We were able to find a solution for something like this, an exact solution. So it does work. And we've applied this thing to, this is a bubble that is being stretched in a shear flow. And so you see the surfactant is being advected towards, from the bulk to the interface, so higher concentration. This higher concentration is going to make the surface tension lower, which is going to make the ball break. And you see here the bubble is kind of pointy, okay, because the surface tension is less strong. So this is a qualitative example. And we've also compared this thing to some experiment. If you do this deep coating, where you take a plaque in a liquid and you withdraw it, you have this sort of flow, and depending if the surface is perfectly clean or not clean, you have different dynamics. So here you have a stagnation point that would be on the surface that you see in this experiment, and you see also in the simulation. But if you have some surfactant, you have a point is here in the middle. So you go like this, and then you go like that. The stagnation point is here that you see also in the simulations. So that's it. That's all I wanted to talk about. Give you this thing back here, and I will take some questions.
So how do you determine the thickness of your